All right, so here's where we're going to take a look at some of the group problems that we've done in class. So the one that we're going to take a look at here is one for fluid mechanics. It says, you are the building manager for an apartment complex downtown. The building you manage is 7 stories tall, about 25 meters. The tenants on the 6th floor and above have complained about the water pressure and that it is too low. That's a typo. It's supposed to be just the 6th floor. The 7th floor is actually an attic storeroom, so no one's up there. They want the water to be moving at least 3 times faster when it comes out of the faucet, or they will move out. You currently have a pump that provides water to the entire building. The pump is at ground level, and so we've got a building here. It's 25 meters tall, about, and over here we've got a pump at ground level. Let's see, the pump is at ground level and supplies a pressure on the water. So the pressure down here at the pump, in fact, I'm going to draw this here, it's a water pump. It's connected over to here and it goes up to the 6th floor where we're having problems with water pressure. Say in the shower or doing dishes or something like that. Important to have some water pressure there. So here's what we're going to do. We're going to have point A here. We're going to have point B up here at the shower head. All right. The shower head at the 6th floor is at a height of 20 meters above the water pump, which means the point that I'm looking at here at B is 20 meters up. As the building manager, you decide it would be best to put a small water tower on the roof of the complex rather than buy a much larger and expensive pump. How high must the top of the water tower be in order to satisfy the tenants on the 6th floor with 3 times faster water? Now, the idea behind this is most of the time regular people don't refer to water pressure in terms of PSI or pascals or anything like that. What most people usually describe as water pressure is usually how fast the water is going and how much of it, but a lot of times how fast it's going. And so if we have water that's kind of dripping out, that's not a lot of water pressure. If we have it moving much faster, then that's going to be a decent amount of water pressure. So the tenants are giving a request in a very real world way. They say, it's moving too slow. I bet if it were moving twice, maybe 3 times would be best. Faster, we'd be pretty happy. That would be pretty good water pressure from regular people talk. So one of our first problems with this is to solve their problem. Well, we have to know how fast the water's going if we want to try and design it to be 3 times faster. So the first step that we need to do is we need to find the water speed at B. Now, all of this is based off of, well, effectively conservation of energy. We're going to apply Bernoulli's equation. And how we're going to do that, I've already set this up where we have 2 different points. I'm going to say that the height at point A is equal to 0, and the height at point B is equal to 20 meters. We also know that the pressure being supplied by the water pump down here, you can imagine that we have water here, and the pump is squeezing it, and it is squeezing it with a pressure of 306,000 pascals. About 3 atmospheres of pressure. Now, these are just numbers that I've put together that probably don't necessarily represent fully real life. There's a lot of stuff that goes into designing a full sewer system here. That includes things where you have pressure losses from what's the equivalent of friction and a few others. But for our purposes, these are the values that we've got for this problem. We're going to kind of do this in a hand-wavy, ignoring things like friction approach. All right, now, we're going to apply Bernoulli's equation, and Bernoulli's equation basically says that the pressure at a given point, say A, this is the fluid pressure, how much we're squeezing the water or that the water is pushing on its surroundings, plus the dynamic pressure, 1/2 rho VA squared, plus the hydrostatic pressure, rho GHA. All of these together equals a constant that is the same for our fluid basically anywhere in the flow or anywhere in what we're working with. Now, the pump, we're going to say that it has a very large water supply, and so the velocity of the water near the pump is actually going to be pretty low. fact, it'll be so low that we're going to approximate it to be 0 meters per second. We did something similar with the water tower, and it's decently representative. If we had a smaller supply on the pump, then we might have to go through and account for the water flow in there, but most likely you're actually going to have a large water reservoir that is then connected to the building if you're supplying the entire building. All right. Let's see. Well, we know the pressure at A was 306,000 pascals. Plus 1/2 rho, we're dealing with water, which is 1,000 kilogram per cubic meter. Not 1, it is technically 1 gram per cubic centimeter, but we want SI units. And our velocity at A, the water's not really doing a whole lot of moving. It's moving a little bit, but not a whole lot. So we're going to approximate that to be 0. Plus hydrostatic pressure, 1,000 kilogram per cubic meter, my density rho, times the acceleration due to gravity, 9.81 meters per second squared, times the height at A, which, hey, look at that, is 0 meters. Both of these terms are actually 0, and my Bernoulli's constant, at least right now, is 306,000 pascals. Let's talk about what this actually means. Now, we talked in class that Bernoulli's equation is an application of conservation of energy onto fluids. I mentioned that the dynamic pressure looks a lot like 1/2 mv squared, which is the kinetic energy. Energy of fluid moving, the dynamic pressure, that's going to use up some of the energy. Or not use up, but take some of the energy while the thing is moving. That's where the energy will end up. We've also got that there's something related to energy in how high up the fluid, the fluid is going. This first term, the fluid pressure, referring to how much you're squeezing something, might be best approximated to be thought of as elastic or spring potential energy, where we actually squish something, and so it pushes back out, and it's a lot like a spring. I could squish a spring in, and it pushing will actually help push things out. It's not a perfect analogy, but it's a good way of thinking about this. These are energies, or at least related to energies. If they were actually energies, they'd be measured in joules. Now, a Pascal is what we call, or is the SI unit for pressure, and it is equal to a joule per cubic meter, meaning that pressure is related to energy in that you can look at it as an energy density, how much energy you have at each point in the fluid. But let's look at that even more broadly, just as this is related to my total energy. So you can imagine that the pump is giving this much related to energy, and that energy can then move from either the pressure that we have here, or we could take some of the pressure and lower it and make the water move faster. Some of this energy can move over here, or we could put it into gravitational potential energy, make it go up higher. In short, what's happening is as I move the fluid higher and this term gets bigger, the other terms, or one of the other terms, depending on the circumstances, must get lower. And the same thing for the dynamic pressure. As I increase the fluid's motion, it increases dynamic pressure, and we will see a decrease in fluid pressure or a decrease in hydrostatic pressure if we have it going down some height. This is what we talked about in dynamic pressure when we covered that in class. As the dynamic pressure increases, as it starts moving faster, the fluid pressure, how much it pushes or is squeezed by, will actually decrease. And all of that is related to conservation of energy. You can imagine this as the total energy we have here at A, and what we're going to do is we're going to see that some of that energy goes into raising the water up, and whatever is left over is what's available to make the water go. Unfortunately, we're going to find that it's not enough energy. Or at least that's what the tenets tell us. Now, we found our constant, which might better be described as something that tells us the total energy for our setup. So we know that this 306,000 pascals is going to be equal to the same setup at point B. So pressure at point B plus fluid pressure plus 1/2 rho VB squared plus rho GHB. Here's where we're actually going to have to start filling in some more stuff. The pressure at B, and here's one of the hardest parts, we're looking at the water pressure as we've opened up the tap and the shower's going. which means the water is now leaving the shower and flying through the air. Well, what's it being squeezed by? Over here, we found the fluid pressure by how much it was being squeezed by the pump, which was 306,000 pascals. When it comes out of the shower head, you might think, well, there's nothing squeezing it. But remember, there's air all around us, and air does squeeze us quite a bit. In fact, air squeezes us with atmospheric pressure, we're going to assume, is about 101,325 pascals. This is atmospheric pressure. Plus 1/2, 1,000 for my density of water, times VB squared. I don't know what my velocity is. I don't know how fast the water is going. That's what we're looking for. Plus rho GH, so that's 1,000 times 9.81 times 20 meters. Point B at the shower head is 20 meters up. And all of this is equal to 306,000 pascals. This is related to my total energy that I have. And now I'm saying some of that energy goes into the fluid pressure, squeezing this, and some of it goes into how quickly the fluid is moving, and some of it goes into raising the fluid up a certain height. Okay, let's run some numbers on this. Over here, I'm going to have 9,810, 1,000 times 9.81 times 20. That's going to be added to plus 101,325. And I get the following in between step, 306,000 pascals equals this term plus this term, because those are all numbers, I can find those, 297,525 pascals, plus the term that I can't solve yet, 1/2 times 1,000 is 500 times VB squared. I subtract 297,000 from each side. I get the following. 8,475 pascals equals 500 VB squared. I'm going to divide this by 500, and then I'm going to take the square root. I can now solve that VB, how fast the water is moving when it leaves the faucet on the 6th floor, is about 4.12 meters per second. About a factor of 2. We're looking at maybe 10, maybe 12 miles per hour. Not a whole lot of speed. Not a whole lot of speed. So the tenants are probably right to complain. Good. Let's solve their problem. They said they'd be happy if we change this and get it 3 times greater. So what we actually want, a new VB, we want that to become 3 times 4.12 meters per second. And we want that to be our new velocity at the shower head. So I'm going to say VB, we could call it VB star. This is going to be our new one. It's going to be equal to, well, let's multiply this out. Looks like it's probably going to be 12.36, but 4.12 times 3. Hey, look at that. Let's call it 12.4 meters per second. Now that is probably going to be 25, maybe 30 miles per hour or so. That's going to be a much better water speed, and probably going to please the tenants. At the very least, we can go in and say, we got you what you wanted 3 times more. All right? Now, to do that, let's find what our new constant is going to be. And when I say new constant, we found the old constant with this much related to energy. We can only, at this height, get speed enough for about 4 meters per second. But we don't want that. We want 12 meters per second, which means we need more energy overall, which means we're going to end up with a new constant. We're going to significantly change our system. And how we're going to do that, our plan is to put a water tower up here on the roof with water in it, and the water will come down and now supply the water pressure and water supply for the showers, at least on the 6th floor. Odds are good we'll actually use it to supply a significant portion of the building. but neither here nor there. All right, so let's find the new setup. We know that we want the velocity at B to be 12.4 meters per second. We want our height at B, well, it's not about want, it's where the shower head is. It's about 20 meters up. And we know that the shower is still spraying water out into the air, so the fluid pressure will be 101,325 pascals. With this, we can now find our new, our new constant. Well, if I do that, I'm going to have my pressure, my fluid pressure, I'm going to save a little bit of time here, 101,325 pascals, plus my dynamic pressure, my new dynamic pressure, 1/2 times 1,000 times 12.4 meters per second, quantity squared, plus my hydrostatic pressure, which is actually unchanged. That one is actually going to be 1,000 times 9.81 times 20 meters. When I solve for all of this, this is going to be, let's see, 12.4 squared times 500 plus the quantity of 9,810 times 20 plus 101,325. My new constant is 374,405. Let's just call it 400 pascals. Technically, we could probably just call it 374,000, but let's keep a few extra significant figures for now. All right. Here's the thing. Now we want another point to supply this. Let's call it C. I mentioned that the water tower, even though in real life they don't actually do this for a variety of reasons, but we're going to have the water tower open to the air. It'll just be at atmospheric pressure. That doesn't mean we don't have a roof on it. It just means that we don't have it pressurized. In real life, you would normally actually pressurize it to help keep things clean, as we've talked about in the class. But we're going to keep this simple. We're going to say that it is at atmospheric pressure. All right, what I need to know is how high up do I need the top level of that water tower in order to get me the water pressure I need at the faucet. Now, maybe I don't have to have it where that's the top level. Maybe I can make it where the water tower, that's the bottom part of it. But on either way, what we're actually finding is where do I need the water level to be in order to get this water pressure? All right. Let's see. The other thing that we're going to mention is this. The water in the water tower is going to be really big, so even if I have the faucet going in one of the apartments, I'm probably not going to be draining the water tower very quickly. We definitely don't want to design it that way because we need enough water there to actually supply it for a good number of the tenants. Maybe they all take a shower when they get up in the morning, and so we need something that supplies enough water. So the water tower is going to be pretty big, so even when the faucet's going, like we saw before with the pump, the water level in here probably isn't going to move very much, which means my velocity at C of the fluid speed, is going to be 0 meters per second. HC is what I'm looking for, and we said that we would keep it at atmospheric pressure. All right. So we said that our total constant was equal to 374,400 pascals. And we now want that to come from a supply from the water tower, which has a fluid pressure of 101,325, plus 1/2, 1,000, times, again, the water level is probably not doing a lot of moving in the water tower, plus 1,000 times 9.81 times HC, the thing we are actually looking for. We can now go through and solve for HC. Let's go ahead and do that. See, this is actually, hey, look at that, 0. So I'm going to do 374,400 minus 101,325. I'm going to divide that by 1,000 and divide that by 9.81. Or I could have honestly just divided it by 9,810, which is great. I find, solving this, that the height that I need the water at is 27.8 meters. Now the final thing that I ask is, does this sound reasonable? Well, I need the water level at 27.8, about 28 meters up. Well, my roof is at about 25 meters, so I need the top of the water tower, or the bottom, however you'd like to set it up, to be about 3 meters above the top of the roof. That's not that difficult to actually set up. That seems pretty reasonable. Now, if I had a water tower that I needed it to be 50 meters up, that would not be reasonable. That's not a thing that I would actually build. I'd probably just get a more expensive pump. But this is a very standard way of going about this. In fact, if you take a look at pictures of any tall buildings, they usually have water towers at the top so that they can supply water to the upper levels with a decent amount of pressure. All right, this is how we apply Bernoulli's equation, and I do want to emphasize the idea that this is how we apply conservation of energy to fluids. You can imagine it as the pump is supplying a certain amount of related to energy. It's not actually energy, but it's an energy density, you could say. But some of that gets used up, or put into, I should say, potential energy, and the rest of it could go into kinetic energy. So, this is an application. It's a little bit different because it's not exactly energy, but this is something that allows us to work with fluid mechanics very well.